you were able to access yesterday's. If not, you can always jump in on the on the main branch from not your forked version, but the parent or upstream repo, and try to access it there. So as before, there's kind of this handy link here. If you're looking on the screens, there's this like badge that says Open in Colab, and that will bring you to the same screen that I'm seeing here. Again, to orient everyone, on this left panel, there's a few things here, including a table of contents, which just has like the various headings. You can actually, by the way, look at what files exist in your local Scratch directory. This is so if you run some of the commands, you'll be able to download data and also look at the fact that they exist there. And in this notebook, we actually don't need to use a GPU. I think that might be helpful because, again, Google can be a little possessive of their GPU time and they'll kick you off. So I actually recommend going to change the runtime type. If it's not already set to CPU only, then go ahead and do that. And what you'll see is it will say connect in this corner if you haven't yet already done that. And it will not say connect to a T4 GPU or some other type of GPU, it'll just say connect. Okay. So the goals of today's lesson and tutorial is to look at graph neural networks. And so this is an expanding topic. It's starting to become in vogue. And there's just a lot of new developments. So I can only really give you an appetizer, I guess, for a lot of things that are to come. And I also hope that you can take this and run with this and check out new exciting applications. Again, because my background is working in galaxy evolution, that means that a lot of the examples I'm going to draw from are related to galaxies, and in this case, the large scale structure. So basically, like galaxies and their surrounding environments, even into like sort of the cosmic regime. But you could imagine that graph neural networks, and hopefully you'll see this with the examples, that they can be applied to many different types of systems. Okay, so the goals again, we're going to learn about mathematical graphs. It's not going to be as top down as yesterday's lectures, and that's partly because while we have intuitions for what pictures are, images are, they're just grids of pixels with things on them, like a galaxy or a picture of a cat or something. In this case, graphs are a little more abstract, so I do want to actually provide more of the foundations just so that we're all on the same page. And we want to talk about how they are capable of representing astronomical systems. And then we're going to create a cosmic graph from a catalog data set. So this is going to be similar to the type of data that you saw with Viviana's lecture, but this is going to be a catalog of simulated dark matter subhalos, which are basically just the entities that also contain galaxies in them. And so I won't get too much into those details, but we're going to use a simulated data set. We're going to then create a graph by connecting, basically we're going to connect the dots of the cosmos, and maybe you've seen pictures of things like what I'm showing here on the screen, where you've got, just large scale structure of galaxies in a cosmological simulation, and you can just connect neighboring galaxies or neighboring subhalos. And then finally, we're going to actually we're going to plop neural networks onto this graphical representation and effectively learn the interactions and the effective theories of how these subhalos depend on each other's properties, and try to learn something about the connection between galaxies and dark matter subhalos and their surrounding environments. So a lot of this work is pretty cutting edge. I wrote a paper with Christian Jefferson and presented that at the just earlier this year. So don't worry if this really does seem quite different from the kind of analyses that we've discussed and been presenting recently, but it's actually in many ways once you get the hang of what the point of using graph neural networks are, I really do think that you can start to apply these to other things. So there's a set of references here, and I'm just going to show this picture again. Again, what we're seeing in this image is just a three-dimensional representation. So it's a scatter plot, but projected in 3D, where you've got X, Y, and Z. These are just the positions within a sub-volume of a cosmological simulation. The colors indicate the sub-halo mass in logarithmic units and of solar masses. And what you're basically seeing is that, galaxies or subhalos, again, a galaxy lives inside the dark matter halo in the lambda CDM lambda whole dark matter paradigm. And so under this paradigm, what you expect to see is that sort of more massive galaxies in more clustered environments tend to reside in these higher mass halos, subhalos. And so that's sort of indicated by the color here. So you can see some yellow and orange points, and around them there tend to be more galaxies than, say, some of the objects that are off in the corner here. And again, we're like connecting some dots, and we'll talk more about how and why you would do that. Okay, so setting up the notebook, I don't think there's anything too different from what we did last time. But again, I've got some, installation code, some importing of Python packages, and then downloading the simulation data. So specifically, this is from Illustrious TNG 300, the hydrodynamic one. And so, I think I've removed I've done some data cleaning in here already, because otherwise it would take a long time to organize everything. But it's all just put there in a what's called a Parquet file. And if you haven't seen this before, don't worry too much about it. You should just think of this as like a binary format that quickly, or it's essentially just a table, but it's compressed into a format which is like easier to store and actually very quick to read. And so we're going to open that using pandas and load it into a data frame, just as we've done in previous examples. Sorry, this pop-up keeps showing up here. So if you're able to download those packages, install those packages, that should take about, 60 seconds or so. And so while you're doing that, I'm just going to show, as usual, we'd like to take a look at the data so we have some intuition about, what it is we're going to do with it. So I like to, again, look at the shapes of like anything that's, more than one dimensional. And so in this case, we can see that the shape here is 575,561 rows by 14 columns. So again, those 14 columns in Viviana's nice tabular drawings, like those columns are the features, right? Those are the sorts of things that we know, the properties or whatever about each row. Sometimes you hear people say, a row is an example, or a row is, in this case, a galaxy or a subhalo. But again, like it's very nice to orient yourself into that sort of intuition. Whenever you see like something in the row dimension, those are the examples that you're trying to learn from. You can grab batches, which is basically a selection of multiple rows at a time. And then, on the columns, you've got the features. One thing specific to this idea is that, like, rows and columns, if you transpose the idea, the concepts of them, it does not apply in the same way, because rows are meant to be the same entity, right? Like all rows are, in this case, subhalos, right? But all features are not the same. Some are more useful for certain learning tasks, and some of them we're not even going to look at all. And this is actually really important, because the idea of a graph neural network is going to hinge on the fact that all those rows are equal, or they all represent the same specific entity, right? So you can imagine that in this case, right, we have subhalos, but if we actually had a bunch of rows, and maybe some of them let's say they're all galaxies, right? But in some case, they might be stars, or some of them might be AGN, or some of them might be like totally different things. They might be cosmic rays or something like that. Imagine this is an observed data set. In that kind of sense, then you typically, when you try to do a machine learning task, you would want to throw away the things that are like irrelevant to your task at hand. You would need to clean the data and say, okay, everything that's not a galaxy, I really need to chuck out. Graph neural networks have the potential to also address the fact that you can learn from heterogeneous data sets which contain rows of different types of examples. And so, although we're not going to quite get into that, I just wanted to sort of make that point now. So as usual, it's nice to grab a sampling of the rows, and so you can see and scroll through here. This column has a lot of the feature names are kind of long, so I sort of made a little shortcut function where I just map the feature names and remove the subhalo underscore in front of all of the column names. This kind of thing, by the way, is also quite common. You'll see if, like, when people pre-process data, if they just want to like make the names less unwieldy, you can do something like a subhalos.rename. You create this, which is a dictionary object. It maps the original column name to the same column name, but just minus those first 8 letters. And you only want to do that in the case of everything except for a subhalo ID. So I also have this if statement at the end. So if it starts with subhalo underscore, I want to remove those letters. But if it's subhalo ID, I actually want to keep that because that's a little more meaningful. I have a halo ID. This is subhalos can belong to parent halos, and they're basically like if they're essentially bound to another or larger halo, then you want to keep track of both the subhalo and the larger halo. And again, if any of that is kind of confusing, all I really can say is that if you can go back and look at this picture, you kind of can get the sense that some of these subhalos and galaxies are satellite galaxies of a more central or more massive halo, and that's just called the halo. So I apologize for some of that jargon. I know there's a lot of like galaxy evolution stuff getting kind of mixed in here, but you can now see that I've renamed those columns. I've set it in place, so this doesn't return another data frame. It actually modifies it in place. Axis is equals 1, by the way, is the way that we specify that we want to rename things in the column dimension. If I did axis equals 0, it would try to actually make this mapping happen on the rows. And the row IDs are just these, incrementally incrementing integers. And so that's not really too helpful. All right. And then also, I think Viviana mentioned taking a data frame and calling .describe. I usually, will look at that as well. And you can actually see, there's a whole bunch of numbers here, fine. But one of the things that's important that I noticed is that the minimum positions, X, Y, and Z, are the positions here of each subhalo. Some of these are negative, and so I actually just decided in the next column, the next cell, to subtract off that minimum value so that they actually get sort of reset to 0. That actually will become kind of important later as we're building up the graph, but just for technical reasons. Let me actually quickly go through some of these columns here. So X, Y, and Z are the positions of each subhalo. This is actually determined using a halo finding algorithm. So this is, there's basically another algorithm that needs to go out, look at a dark matter simulation, find collections of, gravitationally bound dark matter particles, and some of them are going to also have galaxies, essentially star particles and other things in this hydrodynamic simulation. And then, it's going to say, okay, this one looks pretty bound. I think that's a real subhalo. And then it's going to give it an ID and grab some properties. So the X, Y, and Z are sort of the centroid locations. Vx, Vy, Vz are the velocities. So this thing has some velocity and some constant frame of reference. The number of stellar particles, so number of star particles, is basically tells you about how resolved it is in terms of the hydrodynamics of the simulation. And the log stellar mass is exactly what you think it is. And same thing with the log halo mass. This is the dark matter. This is the stellar mass and the star particles. There are other things in here they're not in this catalog, but you can imagine also measuring the total gas mass, for example, other types of things, the velocity dispersion, particles. In fact, so there's also a couple other things. There's log Vmax, and this is just the maximum velocity of any particle within within the subhalo. These are just, again, ways that you can describe your dark matter subhalos. Log stellar, half mass radius, and then there's also this Boolean column, which is central, and that just tells you whether or not this is a central halo, or if it's a satellite that's orbiting a different central halo. So it's nice to go and explore some of these data. So we can actually go ahead and I'm going to go ahead and make a small subset of rows here. So I actually made another data frame which I'm just calling DF instead of subhalos. And this is just grabbing a corner of the simulated cube. So 50 by 50 by 50 megaparsecs chunk of the data set. It's because originally we had 500,000 plus rows, and that's a little too many. You kind of can get a reasonable statistical sampling if you just grab, a smaller subset. So in this case, I'm only getting 1,600 or so, and then we can actually plot, the stellar mass against the halo mass of galaxies, and you can also color them by, whether or not that column is central, right? So you can look at central halos and satellite subhalos. And what you see here is, this is kind of known as the stellar mass halo mass relation. This is effectively, what you're seeing is just, if given the halo mass of a galaxy, how much do you know about its stellar mass of the galaxy? And so you're connecting the galaxy to its subhalo. Yeah, this is just scientific context and background. It's also helpful to make a scatter plot as I sort of showed earlier, but you can actually now do it for this very specific data set. And this is exactly what it looks like. I haven't drawn the connections between the galaxies here, but this is just a scatter plot. And in this case, the colors here are showing the stellar mass rather than the halo mass of the galaxies. But hopefully, if whenever you want to make nice visualizations and things like that, it's useful to get a sense of, again, what's going on with your data. All right. So before we take the plunge into mathematical graphs, I just want to check, does anyone have any questions? I'm sure you have some, like, why are we talking about this stuff? But any concrete questions? All right. Yeah. Go ahead.
So we use graph neural networks when we see there's some connection, kind of a practical connection.
Yeah, we'll get into that in a moment. Yeah. And in fact, actually, maybe I'll use that as a launching point. When would you want to do, not even graph neural networks, when would you want to make a graph? What is an example of a graph?
Oh, I know, subway system.
A subway system. Oh, very good. Yeah. Oh, very relevant. Yeah. A subway system is an example of a graph. That's a great example. Yes. So you can imagine subway systems where okay. And so let's go and jump straight into some of the nomenclature here. So oftentimes you'll have a graph, let's just call it G, and it's usually specified as the some collection of nodes or vertices, which I'm just going to call V, and edges. And edges are sort of the connections between them. So in the example of a subway system or a set of train lines, what are the nodes there? Stops? Yeah, the stations? Yeah, exactly. So if we have a subway system, here, let me see if I can do this on the fly. Subways, systems are a collection of the train stops or stations, I'm going to call them. And what are the edges then? I guess that's kind of a weird question. It's just it's just the tracks in between, right? It's like the train lines. So we're gonna I'll call them the train lines. I don't know. Train. I'm sure there's an actual word for that. But so in that case, you can imagine drawing your favorite blue line if you're taking the MFL between the hotel and here. You've got subways, stops along the line. Maybe you've got another line that intersects here, and you can imagine that you're connecting. And I'm drawing all the nodes again in blue here, and then I'm drawing the edges in red. Even though this is not what a subway map typically looks like, I apologize for that. I think it's more useful to just get the sense of this is what's going on here. Okay, that's a great example. Any other examples of graphs, mathematical graphs that describe things in everyday life? Yep.
Social groups.
Social groups, yeah. So in terms of social groups, what are the nodes? People, yeah. And then what are the edges then? Friendships, relationships, yeah, exactly. And so oftentimes, actually, this is one of the first use cases for graphs and graph neural networks is on social media, right? To represent the different types of relationships that people have. And in fact, not just people, but also businesses and other entities, events, right? Like if there's like a Facebook event, you want people to RSVP, it's interesting because you have different types of nodes in that kind of case. And that's another example of a heterogeneous data set that you would want to analyze with graph neural networks. But you can then, friendships or interactions or RSVPs even. There are different types of, ways to sort of connect those. So I'm not going to draw a bunch of connected dots, but you kind of get the idea of what a social group would look like. Another example? Just one more. Oh, question? Yeah.
As a trees.
So what?
trees, an example.
Are trees? Yeah, trees are graphs. Absolutely, yeah. So a decision tree is a graph, actually. Yeah, that is true. If you work in galaxies, a merger tree, which describes, like what happened, like basically the predecessor halos of any given system, and if you march backward in time, a merger tree could be represented as a graph. So yeah, absolutely, trees could be represented as graphs. If anyone had any, caffeine this morning, right? You can think about the molecular structure of, of any chemical, and so chemistry also benefits a lot from graph neural networks, and because just if your typical ball and stick model of different nodes or different elements, I don't actually know very much about chemistry, but let's just say that you've got some sort of let me draw something that looks plausible. Whoops. You can imagine that you have something like that. I don't know, and then let's throw some stuff over here. And so maybe you have like some atoms as your nodes here, and then you can imagine that you've got some different types of bonds in different configurations or whatever, and you want to describe the different types of interactions, like what is this molecule? This molecule has a particular set of properties that describes the molecule as a whole, so the entire graph has its own properties, but every single node has different types of properties as well. So like, for instance, this node here might say like, what type of atom is this? Right, like it could be, I don't know, carbon, it's probably gonna be carbon, or oxygen or something, or nitrogen or whatever, right? Like what type of atom is it? But there are other like properties that it can have on each node, right? You might want to know like what is its, I don't know, atomic mass unit or whatever. You might want to know what is its position, right? And then or its electronegativity or whatever. On the edges, you also can have some semblance of features, right? You can say like, is this what type of bond is this? Is this a I don't let's change the bond. I'm sorry. Double bond. Covalent bond, anyway, ionic bond, and so like there's types, there's something that chemists would do and to describe the types of edge features here. And so, but the concept I'm trying to build up is that you can have features at various different. You have features on the nodes, you can have features on the edges, you can have features on the entire graph, or you can have target labels. Like you might want to predict, given what a description of this molecule, is this toxic? Is this water soluble? Right? Like is the whole graph, is the whole element or the whole molecule, have some sort of property, or does it, you might also say, does this node bond to some receptor, in the human body, and is that, what does that mean? And so maybe you would say like, is this a good bonding site? Is this a good bonding site? Is this able to, interact in some sort of way we want? You might also want to predict like, are these strong bonds? Is this one going to break, given some other sort of external triggers? And so you can make predictions not only on the graph as a whole, you can try to make predictions about each node, you can make predictions about each edge. And so there's a lot of things that you can do. What I'm trying to draw home right now is the idea that graphs are actually very flexible. In fact, sometimes too flexible, and it makes it a little hard to understand, like, how do I even get started? Like, well, if I can learn everything, what am I actually supposed to be doing here? But people are only just starting to really answer that question now, I think. But there is a lot of potential here. So just think about like the realm of possibilities. Think about the types of data that you're very familiar with, because your domain expertise will allow you to see a lot more insights into this that I think haven't been explored. Okay, so on the technical point, we're going to go back to the notebook for a second here. Let me just make sure. I grabbed all this. Okay, so we're going to have to use we're going to use another PyTorch based API or library in Python, which is called PyTorch Geometric, and it's just a handy way of dealing with data sets and that can be basically represented on graphs. Okay, but it's so I want to sort of orient everybody here. This first cell down here is going to describe a data set. Okay, and so the node features in this case, I'm going to call X. So X are node features. And then, and X as in like, that's like the variable that I'm using here. And then we're also going to need edge features, which are actually called edge attributes in the code here. And we actually haven't yet even gotten there. But we also have these edge indices, okay? And so the idea with graphs, one of the interesting things about graphs is that you actually have to, you have to sort of choose your labels, like how do you index these nodes? One of the good strengths and one of the pitfalls sometimes, or at least complexities of graphs, is that you actually, it doesn't matter what order you label these nodes or these indices in, right? Like it's what we call permutation equivariant. The indices in these, you basically can swap the numbers around, like how you label them, and it doesn't really matter. It should describe the same exact graph. So I could say that this is node index 1, 2, 3, 4, 5, 6, 7. I'm sorry, that's probably really small, but anyway, I can like do that, but I could also just arbitrarily switch some of these numbers around. And the is that this doesn't change your system at all. This is still the same subway line, because the properties are still the same, like their locations and how big that subway stop is are still the same. You just decide to give it an arbitrarily different index. And that's the same thing with your edge indices as well. So edge index is just something we're going to keep track of. And so in this case, because I've changed the location of 5 and 1 here, this edge you could call 5, 2, or whatever, maybe you want a comma in between or something. And this one would be like 2, 3 or whatever. And so like the way that we handle our indices is going to be somewhat flexible, but we need to also therefore make our neural networks, our algorithms, to also leverage that flexibility, right? They can't totally break if you decide to change the indices in an arbitrary order. Okay, so I'm going to start to describe a graph here, and so you can specify a graph by its nodes and its edges, and so we're going to do this here with X. This is implicitly saying that there's going to be 4 nodes because each of these has a feature, just a single feature in X. So there are 4 nodes, and they're going to be indexed 0, 1, 2, and 3. And then I'm basically putting together some connections here under edge index. And the way this works is, at least in this particular representation, you're saying that 0 connects to 1, and then you're saying that 1 connects to 0. So this gets to the point that like subway lines, usually you have, if you have a subway that goes one way, oftentimes you'll have like, something that goes the other way. But actually it's not guaranteed, right? So it might be helpful to say that these are actually directed, subway stops. Like there's actually a line that goes that way, but it's, maybe it's not true. Like maybe this one nobody ever goes to this one in a particular direction. And so you can maybe decide not to draw a directed arrow that way. And so the way that we represent graphs is, that we have to explicitly say whether or not, the edges are going to be directed, so going in only one direction, or if they're undirected, in which case that's the same thing as having one going, a directed going one way and then a directed going the other way as well. So in this case, we have an undirected edge between nodes 0 and 1. We have undirected edge between nodes 1 and 2, and then another undirected between nodes 1 and 3. And we then cram this all into something called a PyTorch.data.data, capital D data object. And this is just a class, it's like a Python object, which is pretty flexible. Like you can go ahead and stick anything you want in here. Like I can go and define something called my favorite feature, and I could probably just, I haven't tested this, so let's see. My favorite feature equals torch dot, I don't know, tensor 0. Let's just see if this works. Yeah, okay, I was happy with that. So you can basically like add whatever you want into this. And so I have no indices or anything on this, so this would actually be a graph level feature. But you can also print out data and they'll handily tell you the shapes of these objects. So X are the node level, again, the node level features, and it's of shape 4 by 1. So there's just, there are 4 of them and only 1 feature per node. The edge index is 2 by 6 in this case. And so really what that's saying is, again, there's sort of the 2 endpoints. It's specifying what the 2 endpoints are, and there's 6 of them. Or really, there's actually 3 undirected edges, but 6 of them because you have to double that in order to represent the fact that they go both ways. We're going to look at what this graph looks like in a moment, but first I want to also talk about a second representation. And if you must, oh yeah, sorry, questions.
This could be to like 2.5, 4.5, 1.7, 1.0 values.
Oh yeah, sorry. Yeah.
There are 4 nodes, but what are those values?
Yeah, I didn't really say what those numbers are. They're kind of arbitrary for now. You can imagine that, like, maybe in the case of like galaxies, maybe that's the amount of mass. It's just some number, or it's some property. I haven't actually defined it yet. I apologize, that's being a little abstract. If you scroll down, you can see a little bit. You can see what this graph looks like, and in this case, I've sized it. It's just the size in this particular example, but it could be, could be anything else. Thanks for the question. Yeah. Any other any questions?
So the X is the feature of the node.
It's a node feature. That's right. So X is a node feature, and in this case, it's only 1 column essentially. You can think of that. One feature per node.
So the edge index means like it can go from 0 to 1 or 1 to 0.
The edge index, exactly. So the edge index tells you where those connections exist. Sometimes whenever we look at a node, and we're about to get into another formulation of this, but you can look at the node, you can say, what are its neighbors, right? And that just asks the question, which ones are connected to that node. And so the edge indices will tell you exactly which ones are connected to that node. Thanks for the question. Any other questions? Yeah.
Is there a way to just provide like positional data and have edges being produced, or do you always have to specify the edges?
Yeah, no, it's a great question. Do we always have to specify the edges? No, you can actually build them up simply from algorithmically or however you feel. And in fact, that's exactly what we're going to do. So with the subhalo catalog we just looked at, there are no edges implicitly there, right? We only have the positions. And then we're later going to go ahead and say, let's just connect things that are near each other. So that's exactly right. Yep.
So these are kind of like arbitrary feature values or whatever, but do they have to be values or could they be strings?
Can they be strings? Yeah. They can be strings. That would make things a little different in terms of how we would pre-process the data, because at the end of the day, like when they get to your whatever's doing the compute, whether it's a graphics processing unit or a CPU or whatever, they need to be like numbers, right, in order to do the arithmetic. So typically, if they are strings, they can be strings. You would then want to have some way of encoding those strings into numbers, whether it's like projecting them into matrix, some sort of matrix, and those are usually called like embeddings, or you can use a tokenizer or something that will like break them up into little tokens and then use that and turn that into some sort of embeddings. But yeah, at the end of the day, you do want to turn them into numbers. Oftentimes, when you cram them into a data object, I think you'll have already done that pre-processing step, and it just makes it a lot easier to handle, I think, on this side. But yeah, but actually, it's a good question. I'm not 100% sure. Yep. Mhm. Yeah. Yeah. So in a probabilistic graph model, I would almost consider that to be like just a broad technique of saying how variables are being fed in and where the model lies. If I understand correctly, and maybe the way I would say is like you can interpret a graph neural network or some sort of graph model, in the same way, except that the model is going to happen at the specific place where, oftentimes when you make a probabilistic graph model, you actually say like, oh, this is the model, right? This is like the actual, either a physical model or something like that. And in this case, you would just say like, maybe you have like some inputs, let me just try to quickly sketch that, but maybe you have like some inputs going in, and then you've got some sort of other stuff going, and you've got like your model here, you've got your Y or whatever, you've got sigma, and and then you've got your model here. I would basically say that like, oftentimes like this specific entity is where your graph neural network or whatever can go, but it isn't necessarily related directly to like this other graph formulation. Like this graph basically just tells you what feeds in and what goes out. Whereas in this case, we're oftentimes looking at saying like, we have some data set and it can be represented as a graph. Like the whole thing is a graph, and that's just a useful description to have. So whether it's, something in chemistry or protein folding or something in astronomy, we tend to say that those are like, the nodes are the graphs. In this case, the nodes would be like very different types of entities. And so that's more just like how you would set up the problem. Does that answer your question? Okay, thanks. Yep, one more.
Yeah, I'm sorry, I'm still a little confused. As I understand that you have this hierarchy between the features to make up a graph, right?
A hierarchy between features.
Or like maybe not really hierarchy, but some connection.
Some sort of connections. Yeah. You don't have to. They can all, all the nodes can be totally isolated. That's possible as a graph or even a set.
When would I want to use CNNs and when would I want to use?
Yeah, when would you want to use CNNs? When do you want to use graphs? Yes, great question. I'm hoping to give examples that will like sort of guide that. There's no set answer. And actually one thing you'll see is that graphs are so general that CNNs can be considered a subset of graph neural networks. Like transformers, which are used for natural language processing and text data, can be seen as a type of graph neural network. Graph neural networks are almost like a little ambiguous because they're so encompassing. It's just a general, like what I would say a graph neural network, or really just a graph in this case, a graph network is something that describes entities, like objects, right, which are happening on nodes and their relationships. That's it. Anything that's got you where you have like something that's an object, and it has properties and it has relationships potentially with other objects, those are describable using graph networks.
But that's all astronomical data.
It is, but it might not be the optimal astronomical data. So for instance, if I had, if I'm doing a fluid simulation, it would probably be a little intensive to say, I'm going to use every fluid element as a, like every little particle as a graph, as a node on a graph. But, to counterpoint though, sometimes people have used fluid simulations where they make a mesh of fluid, and then they'll take into account the local density and other types of, properties of the fluid on a mesh, and then they do stick that on a graph neural network, and that has shown to be quite successful. So it's you do have to be a little creative sometimes thinking about what the the pros and cons are of representing something as a graph. I don't think it's profitable to just say, oh, cool, I learned like a new tool, like graph neural networks. I'm just gonna go and like, hammer every problem into a graph because I can. It's probably helpful to think critically about, where you would actually see this being a useful representation. And so in the example of like a merger tree, that is like an interesting, that is an interesting and kind of different way to think about things, especially to see it as a graph. I would say that like looking at large scale structure in the cosmos is also another way where you can, kind of intuitively think of galaxies or subhalos being near each other and having, we know that there are correlations between properties of galaxies on very large scales, beyond 1 megaparsec. And that is beyond sort of the typical binding, the virial radius of a galaxy. And so that's another interesting way where we can use graphs to sort of illuminate what the large scale structure correlations of galaxies are. So yeah, I know I didn't like directly answer your question, but I think that if I were to say something, it might be too limiting. I really do think that there is a lot of representational power of graphs, and like I wouldn't get an image and then put it onto a graph, because convolutional neural networks do exist and they're already well equipped to leverage how that problem would be described. Graphs are not as intuitive or useful in that sense, but they can be. All right. No other questions. I'm going to try to get a few. I'm going to try to get through these first two examples. Or there's a few quick exercises, I think, and we're going to just do them. I'm going to give one or 2 minute breaks. But first, I want to talk about another formulation, and it's called the adjacency matrix. And what this describes is really the edges of the graph. The adjacency matrix basically just tells you for graphs, like the nodes on a graph, how do they neighbor with each other? And I bring this up because anytime if you study graph theory, first thing they're going to have in page 2 of the book is going to be like, this is the adjacency matrix of a graph, and so you're just going to see it everywhere. So it's usually represented as an A, capital A here, and in this case there are implicitly indices. So index 0, 1, 2, and 3. Is happening on each column and for each row, and for so for each position, each element in this matrix. So in this case, this would be A 1 0. I guess it depends on if you're looking at this as an array or a matrix, but the idea is that this would be a 1 if there is an edge between those two nodes, given by those node indices. So implicitly, there's also node indices, right? Which I didn't describe in the code, but those are sort of determined by the ordering of the node features. So so this is the adjacency matrix of the same graph that I just entered into the code cell above, and it's equivalent to this edge index representation that you see in this blurb of text right down here, which is also in cell above, the same one that we just had. So we crammed that one into the data object, but basically this is a sparse representation of that adjacency matrix. Any questions about the adjacency matrix? Yep. That it's is it by chance that what that it's symmetric or is it by chance? Actually, great question. It's not by chance, and it's because all of our nodes are undirected, right? Or sorry, all our edges are undirected. So if we had directed edges, if they didn't go in both directions, then you could imagine that whichever way they don't go, then you have to put a 0 in the matrix there. So it's a great question. Yeah. So the fact that it's symmetric means that this is an undirected graph. Yeah. Sorry, I think I saw, I don't know who's hand first.
So
Yeah.
I'm just wondering, how do I actually feed it? So if it's row and then column, which I guess the bottom half does that. Say for example, so row 0 and column 1. That means it's going from 0 to 1 or from 1 to 0.
Yeah. I am not 100% sure. It's certainly one or the other. The reason I'm not 100% sure is because NumPy and Torch and basically all Python arrays are it's a row major rather than column major. So I always get confused with this. Frankly, yeah, I would have to refer to the documentation every time for that. That's kind of annoying. So sorry, I'm not sure. You could probably actually, I think you can actually check if you make an edge index and you make a data object. I think you can actually pull. It's one of the implicit attributes that gets created is the adjacency matrix. So you might be able to figure that out. And I just come back. Oh wait. Okay. Yeah, you might be able to do like a data dot, I don't know, adjacency matrix. Okay, nope, it doesn't have that. I don't know. Yeah, you'll have to take a look through the documentation. But yeah, good question. Yep.
Yeah, I was just gonna ask, you don't formally have to type in all the images, like, to somehow just do it, 'cause
Yeah.
I imagine if you have so much data, you're gonna go crazy.
Yeah, that's right. That's right. You typically won't have to specify them by hand. What's helpful is oftentimes coming up with a heuristic or an algorithm or something that will create those the edge indices. And so in the example below, we're going to go and do that, where we just use we actually use another algorithm called a KD tree, which basically is just in short, it's a way of determining positions and what's nearest to it, right? And so it's a way of like quickly, finding things that are spatially close by close by in the feature space that we try to search in. Yeah. Any another question? I think there was. Oh yeah.
So we will get all the time this matrix, whatever the number of pages are. The structure of the matrix we will get all the time.
Do we get this all? Do we always have an adjacency? Yeah, so this tells you a couple of things, right? Like for instance, it tells you, so this is V by V, where V is the number of nodes, right? So that's the node dimension, and then the number of the number of ones in here is going to tell you how many edges there are, at least how many directed edges there are. So yeah, from the adjacency matrix, you can quickly at a glance get a sense of not just the number of nodes, as we said, the number of nodes and number of vertices, but also what the connectivity of the graph is. So which ones neighbor each other. Yep.
Is the connectivity fixed from start, or is there some way that it could change over time?
Yeah, it's a great question. Is the connectivity fixed? No, it doesn't have to be fixed. So with PyTorch geometric, you have a lot of options in how to like run your neural network. And one of the things you can do is actually like you can have nothing connected to each other, and you can at every single pass through the neural network, check to see which are its neighboring nodes, and then use that to somehow determine whatever the neural network uses. So you could imagine, for instance, I don't know if it's actually a good idea, but you could imagine like doing a particle simulation where you're actually updating the positions, and because you're updating positions and the momentum and whatever, you're also you have to constantly create new edges. And so you might just want to query those on the fly and actually change the connectivity of the graph, since things that are neighboring will no longer be neighboring spatially. But yeah, thanks. Good question. I'm going to go ahead and jump into, let's go note some quick properties. I mean, so I think we already said some of these things about adjacency matrices, but just to reiterate, if an edge exists in that between the two, indices, the two node indices, I and J, that specifies the edge index, IJ, and it will be 1 if an edge exists there, and a 0 if it doesn't exist there. So in other words, if we go back to our subway example, we don't have any edge between these two things, which basically means that these are not connected in the adjacency matrix formulation. So we would put a 0 there in that element of the adjacency matrix describing the subway system. Number of non-zero elements, so elements that are 1 is equal to the length of a row in edge index. Oh yeah. So the edge index formulation is sort of the sparse representation. So the number of elements in each row is going to tell you how many directed edges there are, and because it's symmetrics, as Marcus just mentioned, like that means that clarifies that it is a undirected or bidirected graph. That's another term. This is sparse, which is whatever technical regions. And in this case, we don't actually have any nodes connecting to themselves. So you'll actually notice that the diagonals are all zeros. Sometimes, and actually often, it sort of depends on your problem, but it's oftentimes to create what's called self loops. You might just, and this is just more of like it just happens to be useful for the training neural networks here, but it can sometimes be useful for each node to also have a little loop that connects to itself. And why you would want to do that just sort of mostly depends on, you know, how you like want to set up the problem and whether or not it's useful. And if you design your neural, you can design your neural network in a way where self loops aren't needed. So that's just sort of like an optional thing, but you know, I just want to mention it here. Oftentimes people do use self loops just for like, just to add that extra level of connectivity. It's also worth noting that if you look in a graph theory textbook or any math textbook, you typically see things that are one index and column major because they use matrices. Here we're using Python, it's zero index, it's row major, which means that there are a lot of weird transposed, you know, things. And it screws up your intuition. I admit, I get caught up by this all the time. I'm like, why is this, you know, like, why is this matrix the wrong dimensions or something like that? And it's because I need to take a transpose somewhere. So don't worry if that happens, it happens to everyone. Okay, let's go ahead and draw this graph. And so you can see here, we've got the, make it a little smaller. We've got those, you know, the 4 nodes that we had specified before, and the 3 undirected edges here. So the first exercise is the question, based on, you know, the code above and also from this picture, which is the node index that specifies this central node here. Maybe you can look here. The second? Yeah, the second column or row in the adjacency matrix. Yeah, and why is that?
The row and the columns for it are all ones.
They're all ones. Yeah, exactly. Yeah, exactly. Yeah. So that one is so I'm gonna stick with one. Sorry, 0 indexing. So it would be node index 1. But yeah, that's right. The second column or row in there, and it's connected to all the others. And so yeah, absolutely. That's the reason that this is, you know, node index 1. And you can see that there are, you know, I forget the indices for each of these, but you'll have, you know, connections that are like between index 0 and 1, 2 and 1, and 3 and 1. And those are present in the adjacency matrix. Okay, so that's exercise 1. Good job. So another question is, you know, can you create a torch data object that contains self loops? I'll give everybody like 60 seconds to go. Oh, yeah, actually, go ahead. Yeah.
I just have a question about what.
Yeah, sorry. Yeah, so self loops are the ideas that nodes will need to connect to themselves as well. So that you would draw an edge that is hard to visualize because it's just the node and it goes back to its own node. But on in the adjacency matrix formulation, what that means is that this diagonal, all these diagonals would be 1.
So, for example, in the edge index, you know, matrix that the tensor that you've given, in the first setup, in the first row, essentially, because you have 1 and 1, so does that mean that they're looping?
Good question. So, the way that this should be read is actually like 0 goes to 1, and then 1 goes to 0. Right,
okay, so
and then 1 goes to 2, and then 2 goes to 1.
So if we wanted to make it self-looping, then we would also like add an element where 1 goes to 1.
Exactly. Yes. Yeah. That's right. So everyone hear that? That's exactly right. So we would go and let's put self loops on everything. So we could actually do 1, 2, 3, and then comma 1, 2, 3, and this will add self loops here to the graph. We don't need to change X at all because the same nodes are there. The edge indices are the only thing that changes here. And in this case, we have now added self loops. I'm curious if it will plot it. Ah, yeah, it does. Cool. So there we go. Now we got self loops. Thank you. Okay, last exercise, and then I think we're gonna hit our break because it's right around 10. Fill in the data.edge index attribute that connects all nodes in this particular graph. So we want something where all of the graphs are connected, or all the nodes in this graph to be connected together. So just to be very concrete, I want you to fill in edge index for this such that you have, every single connection represented here. And I wanted it to be undirected as well.
So when you say undirected, then how it will differ from the previous one? Like, what's the example of undirected?
Yes, the previous one was undirected. Yeah. So it's not different. The only thing that's different is the connectivity.
If it is one way, then it's directed.
If it's a one
Way, then it is directed.
it's directed if it's only one way. Yeah.
So one kind of permutation.
I'm sorry.
It's a one kind of permutation.
Yeah. Exactly. Yeah. You can permute through the indices.
I was trying to do, like the zero with the
All right. Are folks mostly there, or kind of getting the hang of it? Yeah. There's if you look in the answer key, so these drop downs will tell you the answer. So you could manually specify all the permutations of the indices without self loops here. As such, so you could do 1 0, 2 1 3 2 2 0 3 1 and 3 0, and then do the reverse versions of that. There's also a handy function. So torchgeometric.utils has a bunch of useful functions. There's one in which is like add self loops. There's one that's like to undirected. And these are just, if you have something that doesn't have self loops and you add self loops, then it does exactly what you expect. If you do two undirected and you have a directed graph, it will just simply fill in the ones that are missing. So you can only so if you want to be lazy, you can just specify the first 6. If you have v nodes, you're going to have v times v minus 1 divided by 2 sort of unique undirected edges, and so you can just specify some version of that, and then go ahead and use the to undirected function. And then if you draw that, you can see that it should give you something that looks like this. So that does it for the just the basics of PyTorch geometric and mathematical graphs. When we come back from the break, there's some technical notes here, whatever. You can also try to fix your GitHub repo. We're going to go straight into building a cosmic graph. It's going to be a little more lecture-y as well at times, but I hope that we can kind of guide our way through this notebook after the break. Thanks.
You should break the Starting with the fold. See if things break.
Get a good break. There's let's see. There's a couple of cells in here that I'm skipping over. It says final technical notes, so read those, if you feel like it. And we're going to get started now with building a cosmic graph. That's just basically a graph of all these subhalos in the cosmological simulation using PyTorch geometric. Sometimes it's abbreviated like this, PyG. Okay, let me just actually first say that we are going to go ahead and create a new data object, which is going to contain all the features, positions, things like that that are relevant for our graph. We're going to construct the graph, so we have a catalog. Those catalogs tell you something about those subhalo features and where they're located, and it tells you also something about their labels. And in our case, we're going to select certain subhalo features as our x's, and I've kind of written this here. So subhalos, again, think the nodes on the graph. We have x's, which are what we know about each node. Y is the thing we're going to try to predict for each node. So the labels or targets, whatever you want to call it. Also, the node positions, which we're not going to use as our node features because we're actually only going to use this for the construction of the edges. Like, we're going to use that to determine which nodes are neighboring, and then we're going to use that to create the positions here. And then based on the positions, we're going to assign edges between nodes. So it's going to be 0, like in the adjacency matrix formulation, it's going to be a 0 there if there's no connection. And if there is a connection, then we're going to put a 1 there in the adjacency matrix, and we're going to do that using just some code above. And then we're also actually going to have edge features. So edge features in this case are just, as we said, that you can have different types of features, descriptions of properties on edges. That's something that we can have here as well. So for instance, the distance between the sort of the norm of the distance between two spatial coordinates can tell you something about like the distance between them. We can also do the same thing, like, for example, look at the velocity difference between any two objects, any two subhalos, and that might be an informative feature. I also, by the way, just want to go back because I did get a question about, like, why would you use self-loops? So going back to the subway graph that we have here, you can imagine that you're trying to estimate something like the commute times between any two subway stations. And so one thing that you could learn or try to predict, for instance, is like, what is the typical commute times between on each edge, right? So that would be a label on the edge that you could try to predict. But maybe you do know what the absolute distance is, right? Like, because you have the coordinates of these things down. So you know what the distance between any two subway stops is going to be. And so you can, somehow come up with a way to, like, learn that. It's not going to be the same necessarily. It's not just a function of the distance, but it's something a little more complicated because there's maybe terrain or there's construction in certain areas and so on. And that, forces, the distance to not just be a linear function of the commute time. The other thing is that, like, perhaps you need to go and make a transfer at this station here. And so actually having a self loop here, having this edge that loops back on the same node, same station, actually can represent something meaningful, which is like, I need to go up this flight of stairs, go and find, like, where I'm transferring into this other train track and then go north-south. So you can imagine that, like, these can have interpretable meanings. It's just, but you do sometimes have to think about it. It's kind of like with graph neural networks, especially because it's such early days, like, there's a lot of, like, engineering. You have to kind of, like, think about, like, okay, why would I make it in this way? And it's not the absolute, like, only way to do it. You actually can have other ways of representing your data. So it's always helpful to think about new ways to represent the data. The ways that I'm currently going to present may not be the only way, and it may not even be the best way. And so I challenge you to go and ask questions about why we're doing things this way. Okay, so I'm going to scroll up a few cells because I said we're going to go and populate these things into a PyTorch geometric data object. Yep, question?
So the node features we already know from the simulated data.
Yeah.
And the node labels we already know, the stellar mass, or
Yeah. So
Y2 and Y prime.
In this case, we know them all because we're doing a supervised machine learning problem.
And do we need that position, or like the node positions in the program, or it is left out?
Do we need the node positions? You could go without them, but without them, you wouldn't be able to know how to connect the subhalos to each other. Like you wouldn't know which ones are near each other. And so you could formulate a different type of model. So a lot of times, in fact, if you look at, for instance, subhalo abundance matching and other ways where you can estimate something like the baryonic properties from the dark matter properties, they actually make no assumption about the positions of those things. So that is a traditional approach, but it's sort of it's unclear why you would want to put that on a graph, because you just don't know how to connect any of the nodes. It's just basically a set of points, like an arbitrary point cloud. So yeah, it's possible. You could try it out and see what happens, but yeah, we wouldn't have any edge indices or features, so it would probably be a little, it wouldn't be much of a graph problem, I guess. Yeah. Okay, so the first thing I'm going to do here is just impose a cut on subhalo dark matter mass here. And so I'm just going to say 10 to the 11, which is, like within the resolution limit of the simulation. So anything above this, you'd certainly expect them to be like reasonably well resolved. I also just want to make the data set smaller because it might take too long. So we go and make a copy of that data. This is sometimes important, by the way. You like whenever you make cuts on data and then you like do other operations, you want to be careful of whether you're modifying some like other data frame that's just being referenced in memory, or if you actually make a copy in memory and this is now an entirely new object. So I'm going to go ahead and do this and make a copy of it, because otherwise if I change df and I add rows, add columns and do other sorts of things to it, it can sometimes screw up the original data frame. Okay, so we're going to go and get our x's, and in this case we're going to use two input features. We're trying to estimate from the dark matter properties, like what is the stellar mass of the galaxy. So from the dark matter halo's halo mass, this is something we had as a column, and then log Vmax, this is the maximum circular velocity of any particle, and it's commonly kept track of whenever you make these dark matter halo catalogs. The intuition, by the way, for that is that these two properties tell you something about the mass tells you something about the binding energy, and you also know something about the angular momentum to some extent from log Vmax. But it's sort of it's a very informative property that's commonly used when you learn about the galaxy and dark matter halo connection. For why as we said, we're going to try to predict the stellar mass for galaxies. So again, to go back, we made this plot. This is the stellar mass halo mass relation. So we're kind of trying to predict this y-axis, and we're going to use the halo mass, which is on the x-axis, and we're also going to use the log Vmax, which is it kind of scales with the halo mass here. So that's our x's and y's, and in a moment we're going to put that into the data object. We are now, this is kind of the tricky part, but this is actually where we're going to go and make all the indices. The edge indices here, okay? So what we're going to do is we're actually going to choose a linking length, and we're going to say, this is all, by the way, in the units of megaparsecs. And so the positions in X, Y, Z are going to be in units of megaparsecs. The whole box is 300 by 300 by 300 megaparsecs for illustrious TNG 300. And the linking length we're going to choose is 5 megaparsecs, but feel free to change this to anything you want. Well, no, not anything you want. Change it to something less than like 10, because otherwise it's going to take forever. And the reason for that is you can imagine if you have like a whole bunch of structure, if you connect everything within like 100 megaparsecs of each other, you're going to have like an insane amount of, you're going to have a huge amount of connections there, and that's not going to be a good it's going to be really computationally expensive. So in this case I chose 5 megaparsecs, and then as I said, we're going to actually use an algorithm called a KD tree here, k-dimensional tree. I'm not going to go into how this algorithm works, but you should just think of it as an efficient way to find neighboring things based on those positions. So, and this is bundled into SciPy. I think there's also a version of PyTorch, but I just used the SciPy one because I'm familiar with it. And, it has these hyperparameters here, but again, I'm not going to go into this. This is just like an object that is initialized using the positions here. And then we also have to tell it how big the box, like the entire box size is, the volume of it. And from that, we can actually get basically the neighboring indices, right? This is exactly what we want, which is edge index. And edge index here is, a KD tree that if you call KD tree dot query pairs, it basically for any index, any node index, it will try to find the pair, like which is within a linking length of 5 megaparsecs that we specified. And in this case, we just said we're going to output a NumPy array, and then we later turn that into a PyTorch tensor. There's some stuff going on here. Actually, let me go ahead and just show you though what this looks like, or at least the shape of this. So when we query this, we actually get something that's in the format. It's got 4 million rows and 2 columns. But if you recall from edge index above that, we actually need to take the transpose of that. So that's actually what we need to do, because that's just the way that PyTorch represents it. So the second part of this code is actually that we need to do 2 things. We need to make them undirected indices, right? Because actually in this case, we're only getting one side of the pair, but we actually need to get the reverse pairs, or aka make those edges undirected. So I do that later. But the other thing that we need to do first is turn this into a PyTorch tensor, take the transpose of it, so make it from 4 million by 2 to 2 by 4 million. So it goes from a really long and skinny, or sorry, really tall, skinny array, and then we make it a very long array. So that's what the transpose does. And actually, this is important, is you need to call dot contiguous. So actually, when you take the transpose of it, it's no longer contiguous in memory. That is, like, things that are near each other, that array is actually all fragmented throughout memory in a non-trivial way. So calling dot contiguous is really helpful, because otherwise this can be very, very slow. That's kind of like a annoying gotcha, but like just I think I mentioned this in one of the technical points in the notebook. You'll want, whenever you see something that's the wrong shape in a NumPy array and you want to turn it into a PyTorch tensor, always call .t for transpose and .contiguous to make it contiguous, connected, that is, in memory. And the last thing we need to do is, because these are indices for some strange reason, I think, let me go and call this again, edge index .d type. What type of data is it? It's in 64-bit integers, but we want to make a PyTorch integers, which is under torch.long. That's just a technical point again. Yes. Sorry, is PyTorch calling the? Unfortunately not. No, PyTorch is also row major, but it is just, it does need to be in the format of like a tensor, which is of shape 2, 4 million. Kind of see that in the example that we had above. Also, so this is like another example, right? Like if we did it this way, which is what the current outputs look like, that is not acceptable for PyTorch geometric to process. And so what we need to do is put it in a format that looks more like this. So this is 2 by, I don't know, 12 here. And in our case, we want it to be 2 by, 4 million. This is kind of just like, like you have to maneuver some of the shapes. It's not clear that you have to do it this way. Like when they wrote the code, they just had to make a choice somewhere, and they decided, I think, to make it, essentially a very long array. Yep.
How many objects are there? I think it's 350,000.
Yeah, good question. So yeah, so if we call that, you can see down here, there are 350,000 nodes specifically. And then in terms of undirected edges, we saw that there were 4 million. And then you multiply that by 2 because there are 4 million undirected objects, but because it keeps track of directed objects, it actually doubles that number. So there are actually 8 million edges in this graph.
Why the number is different?
Why are the numbers different? Yeah, so I mean, if you think about it, the number of nodes in graphs you would expect there to be, like, in terms of the nodes, that sets a maximum value on the number of edges that are possible. And so, right, so if you connect every node with every single edge, then it would be of order, the number of nodes squared would be, but in our case, it's sparse, so they're not all connected to each other, and it could be just some number less than that. It could be as low as 0 if you have no connections, or it could be like very, very low. The fact that it happens to be in the same order of magnitude is probably not fully coincidental, but it's probably useful to pick a number, a linking link, such that you end up with a reasonable, like same order of magnitude number of edges as you have nodes, or maybe like within a factor of a few or something, few orders of magnitude. If you had, if you have 4 million nodes, though, you really don't want to have 16 trillion edges. Like that just wouldn't be like computationally feasible. Good question. Does this include self loops? I actually don't think it does. Good question. We can see what happens if we try to add self loops and see if self. Yep. Or what it's called. So that's from torch geometric dot utils import. Add self loop remaining stuff. Yeah, let's just see. Actually, I think add self loops also might predict some other thing edge attribute. Let's just try this. Oh, sorry. Okay, I've broken something. Oh, I need to rerun all this again. Never live code. Okay, it did not have self loops because we had 4 million, and we got like 8 million, and then we added another 375,000, which is the number of loops. So I guess I didn't have self loops in here. Oh, okay. Huh. I didn't realize that. So thanks for checking. We're gonna see how this runs with self loops. But yeah, anyway, again, a lot you have the freedom to make these kinds of decisions, right? You should probably justify these decisions or run experiments to verify that you're making good decisions, but you have the choice to to make a graph neural networks without self loops and see what happens. We're going to see what happens with them. All right, and then so we've now determined the edges, which means that we now know the connectivity of the graph, but we actually haven't slapped any attributes onto there or any features on those edges. And so what we're going to do here is this is just kind of, this is just like some array magic where I'm taking the rows and the columns, which are determined by the edge indices, right? So remember that the edge index, this is like the position of all of the, positions I and all the positions J, and you're just making like a long array of both of these or a long PyTorch tensor of both of those. And then I'm actually going to go and take the distance by using those as indices into the positions, which are just going to basically get you the position of node I, position of node J, and then compute the Euclidean distance between the two. So that's what's happening in here. Torch.tensor this right here, np.lin alg gives you the L2 distance or the Euclidean distance here. We're doing it along the first axis, which means that we want to condense in the X, Y, and Z coordinates. And then we basically, this is another technical point, but you sort of want to reshape it as like if you have 8 million edges, you want it to be of shape 8 million, 1. So that's what's happening here. So this is now a very, very long, column vector of distances between all of the points for every one of these edges that exist. Does that any questions on that part? I know that this is kind of like a technical formulation, and maybe you haven't seen like a shortcut like this before, but it's really fast and memory efficient. So that's what we're going to do. And then we can actually do the exact same thing with the velocities as well. So we're going to get the sort of the L2 norm of the velocity difference. So the absolute velocity difference sort of for any two subhalos, we're going to add that into as a feature. Finally, we're going to concatenate those features, and we're going to get this edge attributes, or basically edge features. So just to recap, let's go ahead and go back down now to our data object. We have our node features. What is the shape of X here? Does anyone remember? Oh wait, actually, I just realized it's shown right down here. But you can, but yeah, this is a good exercise to have, right? So there's 350,000, right? 350,000 subhalos, and then how many features do we have? 2. Yeah, what are they? If I remember, halo mass. That was like a weird combination of a lot of things, syllables. Vmax, yeah, Vmax is the other one. So halo mass and maximum velocity. Yep. So this is going to be a shape. Yeah, I'm not going to write it. It's going to be 350,000 or so by 2. The edge index is sort of transposed, so you know that this always has to be a 2 because it's where we've got pairwise edges between a pair of nodes, and then we have 8 million here, or now actually 8,300,000, 375,000, and then for the edge attributes we have okay, this is a good catch. So this is not good, right? So the number of edges and the number of features on the edges is not the same. Does anyone know why that happened? Yeah, exactly. Yeah, I added self loops, but I also did it in the wrong order. I have to do that after I compute these edges. And actually, edge attributes and never live code. Okay, let's try this. I probably have, okay. Another problem with Jupyter notebooks is they're stateful, so I'm not actually, it's not clear to me what variables are in what, in what state. So I'm going to go and just run all these again. Let's go run that, and let's see. Yay, they're the same shape again. Okay, so edge attributes. Now we have edges for every single one of these, and then we have 2 features on the edges. What are those 2 features?
The self loops when we are doing the problem. So it depends on the problem, or it's on our choice. Right?
It's your choice. Yep, it's your choice.
Will it affect a lot in the graphical neural network if I do consider self loop?
I don't know, actually. I mean, it really will vary by the problem. Will it affect it tremendously? I'm not sure. I think generally, like in a lot of physical problems, no, I don't want to give. I have no idea. I really don't know. I think it can vary a lot by different physical problems, but it also depends on how you design your neural network. So so the short answer is, you should see.
For example, this subhanel. So they are like really far apart. Self loops might create error. I don't know.
Yeah, I mean, the soft loop has a very specific meaning, and we'll see when we make the neural networks. But the idea is that you will go and pass along information along edges to different nodes and update hidden states. Basically, you're going to have a representation of something, which are numbers, like features and whatnot. And the types of learned features, will depend on the connectivity of the graph. Okay, so what are the 2 edge attributes that we have here? Does anyone remember? Position related to the positions. Distance. Yeah, that's right. The distance between positions and velocity difference. Yep. That's right. So those are the 2 features. Like basically the distance, kind of an abstract distance in space and also in velocity. And then y, what we're trying to predict here is log stellar mass for every one of these. We also, by the way, we can stick the positions in here. We're not going to use them, but again, as I said, we can add any attribute we want. Yeah.
Can you explain again how so the KD3 gave us about 4 million pairs that are within that distance limit?
Yeah.
How did that end up being turning into 8 million edges?
Yes, because those were directed. So though they, like for instance, if they linked node 0 and 1, it would not do the opposite. It would not link 1 to 0. So we had to do that ourselves. And so
the edge attributes here,
yeah,
they have repeat effect.
it actually does repeat them. Yeah, it's redundant. In fact, yeah, that's right. That's absolutely right. And so, so we did the 2 undirected here. Yeah, exactly. Okay, So we now have our PyTorch geometric data object, and we're gonna get ready to start training some models, okay? It's at 11, so we got an hour. We're gonna go and try to zoom through this. I'm gonna go ahead and actually break up into a training and validation data. I'm gonna do it by location because I can't just choose arbitrary columns from the original data frame, or it's not columns, sorry. I can't choose arbitrary rows from the data frame because they're actually linked together by position. They're correlated, right? And so one way that I'm going to do this, there are probably other choices that you can make here, is that, well, firstly, I'm going to actually, in the X and Y coordinates, I'm actually going to restrict it just to like a 50 by 50 megaparsec little pencil beam through that because it's because otherwise there's just too much data and it'll take a little bit longer. But also in the Z dimension, the spatial Z dimension, I'm going to say everything that's less than 200 kiloparsecs or 200 megaparsecs in the coordinates, I'm going to put into the training set. I'm going to create a little buffer zone of 10 megaparsecs because we linked everything that connected on 5 megaparsec scales. So I want there to be a buffer zone that's equal to 2 times that buffer, that linking length, just to ensure that I'm not contaminating my training and validation sets at all. Like they really don't know about each other. There's no overlap in structure. And so I'm going to go from 210 to it's like 302.6, megaparsecs. It's like how much is in the box. So, like something like 92 megaparsecs by 50 by 50 is the size of the validation mask. If you are familiar with NumPy, there's a convenience function which lets you grab the indices based on a mask that you've created based on a selection called mp.arg_where, like the argument where or the index where something is true, and the where is specified by this mask. For some reason in PyTorch, this is like really complicated, and that you have to make this really ugly expression, but that's just the way you do it. Torch.tensor, you get the values of this here, and then you have to like do this dot non-zero function, and then you return it as a tuple and grab the first one. As far as I know, that's the best way to do it. Maybe there's a better way, but anyhow, I can then check to make sure that the indices, and let's take a look at these indices as well. They're just, these are just the indices in the nodes where these are, where we're going to train and where we're going to get validation. And we want to assert that the set of all node training and validation indices is the empty set, aka they do not overlap. And indeed that's true, otherwise it would have thrown an error. So we're good. We have not accidentally set up ourselves to cheat, and we're going to go ahead and train a baseline model. So before we train any graph neural networks, we're going to quickly go back and do something with scikit-learn, which hopefully you remember. You can get a little more practice here. You can choose your favorite scikit-learn regression model. So I'm going to choose a random forest regressor. Actually, did Viviana talk about random forests? She did. Okay, good. Yeah. So so an ensemble of decision trees. So you can load that from sklearn.ensemble and then grab random forest classifier or regressor. We're going to provide it 25 decision trees that's going to learn from. You could do more or less, and you can call fit on that. And so that's exactly what we're doing here. We've specified the training and validation split over here, just sort of to help out scikit-learn. It's a little different than PyTorch geometric. And we make our predictions, and then we go and we can now plot our outputs. And you can see this is the predicted log stellar mass, and this is the true log stellar mass. And then it's colored by the log halo mass. And what you can see is this pretty nice prediction, right? Like this is actually pretty good. We can get the root mean squared error, and using the random forest, that's what this title says, up to or down to 0.186 dex or so. You'll probably find some scatter in this. But this is good, right? Like you always want to train a baseline model. I would say don't go and use like really, really hardcore machine learning models if you don't need to, right? We're able to train this random forest model in this case in, it says 0 seconds, but I don't know how long it takes to optimize, but it's a very, very powerful technique. Random forests are really good. Other types of tree models are very good. Gradient boosted trees and other types of those models are just really good baselines to get a sense of like what is the score that we may try to beat. Because if we do this and then we spend all of our time building like a really complicated graph neural network and we make incremental benefit, then maybe it's not worth it. And indeed, we'll see whether or not we can make a bunch of jump forward here. Any questions on the random forest? All right. So we're going to go ahead and create a simple graph neural network. So this uses something called SageConf. Oh, I didn't actually wanted a link to it here. Here. So SageConf is a neural network layer that's used for graph neural networks. Okay. And I basically just created a simple neural network here. Simple as in like it's just not that many layers, but there's still plenty going on here where we're going to go and try to leverage the information only from the nodes. We're not really going to use the edge attributes yet, but we'll do that actually later if we have time to hit that in the more complicated GNN part. But what we're going to do here is, given our graph, let's go and draw like some. So we've got nodes which are, let's say we've got something like this. This is like a galaxy or a subhalo. We've got that. I should have made those red. And what we're going to do is we're going to try to learn, like what we're trying to do is we know this, the subhalo properties for these galaxies. So we're going to try to predict their stellar masses for each of those. So what you do is you start off with, let's just look at this particular node here. We're going to call that I. And then we're going to call this one, should use red. Sorry, I'm like losing track of these colors here, but let's go and call this one J equals 1, J equals 2. And we'll say this is actually not connected to that. So this is just totally irrelevant, but I'm drawing it here for completeness, right? And so what we're going to want to do is for node I, we're going to have our features xi. They're going to go and feed into some sort of model, GNN, right? And we're also going to want to take into account, some of the other features from some of these other nodes. So in this case, I'm going to call this xj. And what's going to happen is we're going to go ahead and find all j such that j is in the neighborhood. Sometimes you'll see it represented this way of node I. So anything that's connected to I, we're going to do this for all j. And we're going to go ahead and we're going to try to somehow aggregate that information. And this is kind of like, you'll see this operator, this like 0, or so the circle plus like a plus sign in or something. And you're going to basically aggregate all the information over all j that connects to, I. And then you're going to go ahead and feed that into the GNN as well. So in other words, we're going to go ahead and grab the features that are here on node I. Right, so this has feature xi. This has feature equal to x, and I'm going to say j equals 1. And this has feature xj equals 2, right? So the sum of masses, etc. We're going to, for the case of the graph Sage network, what it does is we're going to have some learnable parameters. So we're going to say basically, it's called a convolution layer, but the reason it's a convolution is because it interacts with its neighbors. So don't get caught up too much on that name. It's just a particular algorithm. What we're going to basically predict is some output, which I'm going to call H for now. Actually, I'm just going to call it output. Out equals, and it's going to be a function of xi plus a function of f2 of all x j equals 1 and j equals 2. And the key to how graph neural networks operate in almost all the cases that we currently see is that you can specify this in some sort of way, but you want part of this function, this learnable function, in fact, to know about its graph connectivity and operate on the nodes that connect to the one of interest. So right now we're making a prediction on, on a particular eye here, but we also want to find the J's that connect to that eye. Okay, they don't have to be additive. You can multiply them together. You can have a very, very complicated formulation that is all together. But this is the particular one that we are going to currently use because it's very simple and it's called a SAGE convolution. SAGE is probably some weird acronym. I don't know. But all this is a weight matrix. So this is a a tensor or whatever times I xi plus, and in this case I think it's, let me see if I can find it. You take the W2 a second weight matrix times, and you're just going to take the mean over all xj for all j. Okay. And in this case, we said that we somehow need to aggregate the information. So in this case, like we have xj equals 1 and xj equals 2, right? And so what we're doing here is we're taking the mean of the surrounding things. I'm going to just take the mean of that. We're going to multiply by some weight matrix. We're going to take this weight matrix, this different one here, W1 or I don't know, and then multiply it by xi, the node of interest, and then we're going to produce some sort of prediction. Okay, and so that's basically the output at the first layer of the graph neural network. This again is kind of like the core part of the graph neural network in this particular example. You can imagine that we don't want to do a plus here, like maybe we don't want to take a mean here. But what we need to have, most importantly, is that this is the mean, right? This has to be a permutation invariant operator. And what I mean by that is that if I decided to call this 2 and the other one 1, it can't change. It can't know about the ordering of these things. So this is a constraint in some sense, but it's also very powerful because you necessarily learn an invariant formulation of your graphical model, and therefore your predictions will be invariant as well. This is great because you can imagine, like, if you're just going to memorize something like, oh, I know that j equals 1, blah blah blah, like then it's not really extendable to like other sorts of data sets where you mess up the ordering of nodes. And that's mostly because the ordering of nodes has no real physical meaning. It's just an arbitrary ordering that you first impose down here. So whereas traditional techniques, like a lot of times people would just like augment their data by shuffling it kind of randomly and be like, I guess they'll have to like learn something that's permutation invariant. In our case, because we're using a permutation invariant aggregation function, so mean, you can take the mean of the thing. You could say like take the max of the thing. That's called like a pooling layer. A mean pooling or a max pooling. Those are permutation invariant. You can take the sum of things. And you can also imagine other types of things. Like you could take more complicated functions and stick them in there. But oftentimes something like mean, sum, or max are like actually the very commonly used. In the case of graph SAGE, I think that the mean is used, and then for some other types of convolution layers, you'll see other ones here. So I created this SAGE. So that's what's happening. This is the SAGE this particular formula, but it's really not that important. You should just think of it as it's a thing that takes. Maybe I'll do 3 steps here, right? So the first thing it does is it grabs a formula. It multiplies this or xi here by a weight matrix. The second thing it does is it grabs all of the neighboring nodes, right? And it grabs it grabs this and this. And so that's all happening right here. Or you can think of it as this. And then the third thing it does is it then aggregates all of those, because we know that these are the only 2 that connect to node I. And that last step is that it computes the mean and then multiplies it by yet another weight matrix and then adds it here. So this now becomes the same dimension, same shape as here, because we're sort of taking the mean over all j and we're left with just a single number that could be added here. If we didn't do that, this would be some arbitrarily, it could be a long thing because we don't know how many nodes will be in the vicinity of node I, so we don't know how many neighbors there are. But in this case, it doesn't matter because we distill it down to just a single number. this matrix multiplication. So, okay, so any questions here? So that's, yeah.
So this is like kind of similar to like a convolutional kernel, but that would be like F1 and F2 are the same like weight matrix. That's one of the old neighboring points.
So it is kind of similar to a convolution kernel, but it's partly actually that, let me think about that. So the convolution is tricky because you're basically, you're learning a weight matrix which operates on, it's always the same shape, like the number of neighbors is always going to be the same shape, right? Because you basically need to take the inner product of a kernel, the morphological feature, and the same shape region, right? You take the inner product of those two things and you say, how similar are these two things? How similar is the underlying input image at that position, you know, with this like 3x3 kernel? And that's because the nodes are all sort of, you know, on a pixel, you can actually just think of it as like, you've got, you know, a grid of points, and there's, you know, connectivity is determined by the fact that they live on this pixel grid. I don't know if everybody can see this, but, you know, like a 3x3 kernel saying, this is my connectivity. Like that's all it's doing. It's saying it's always going to look like this. And, you know, for this node, I'm just going to grab these, you know, 8 points plus itself, whatever. So there's a self loop here. And then it's going to go and say, this is like my, you know, my weight matrix is the kernel that, you know, is 3x3. And then it's going to go and query another position. You're going to grab another example as part of your, you know, batch, which is the way that we do it in graph neural networks. And then, you know, you can scoot it over one slot over and do the same exact thing. And you learn the same function. And so that's, it's quite different in some sense because, like, you know, there are a lot more constants. The structure of how you would train it is a little different. But yeah, conceptually, that's why CNN actually can be formulated as a graph neural network. And again, like, you know, you can think of this as like, you know, what are the inputs? Or, sorry, what are the features on, you know, this particular thing here? Well, it might be the G band magnitude or the G band brightness at that pixel, the R band brightness at that pixel, and the I band brightness at that, you know, of the same pixel. And so this would be, you know, three features at that particular pixel location. Yep.
I'm not quite getting the way you've written things. So, like, you have these two functions, F1 and F2. Right? So you can't you just use like a simple neural network?
Yeah.
As an approximation?
Yes, but they have to be permutation invariant. So that's kind of the key here. So like this part, F2 here, needs to be permutation invariant over all J's, right? If there are no nodes there, then we don't know what, you know, then there's nothing, and that's fine. You just add 0. If there are like a million nodes there, like in the neighborhood, then you need to come up with something that can aggregate all that information. If you have a simple MLP, one of the big challenges is that like it's an arbitrary size, and so it doesn't know, right? Like this MLP must have the number of neurons equal to, you know, some function of how many inputs there are, but we don't know that a priori. So yeah.
Also, that the way for W1 X1, that means your output is linear in X1.
I'm sorry, your output is
linear in X1.
Yeah, actually that's true. Yeah. Yeah, that's a good point. In the forward function, you'll actually see that we call X1 here, we do the convolution, and then we actually call the value over here. So it becomes, so the nonlinearity is applied outside of this. That, you know, you could put it in, you could put it out. I mean, it's unclear. I made it, which is better. Yeah, good questions. Anything else? Yep.
Could you, just like turn on the channel,
Yeah.
give an example, like a physical example where you wouldn't choose like a bidirectional situation? Yeah, is that something that you generally want to avoid because that choice introduces bias, or like what's?
Yeah, no, that's a good question. So in physics, a lot of things are bidirectional, like, you know, as far as we know, like, you know, right, like the forces and all that sorts of interactions tend to be bidirectional. So that's definitely, you know, a good assumption to make. If you're doing like a social network, you might say that, oh, well, like if it's bidirectional, it means that, you know, you're friends versus you're only following somebody. If it's not bidirectional, it's just unidirectional. Or like you can imagine that if you have a heterogeneous data set, you might want to make edges that only, are single directional because of like, let's say you decide to put all the central galaxies as a different type of object, and you say satellite galaxies are different from central galaxies. Then you might want to make some edges which are only directional one way, and you might say like, oh, but the central galaxy is able to like totally disrupt its satellites, but not really vice versa. And I don't know, that's just a choice you could make, but that would be an example in physics of something that's unidirectional. Does that make sense? Thanks for the question. Anything else? And and so let me just go and march through this particular bit, but we've got, so that was actually just the first convolution layer. And the reason I didn't say that this is like why, like this isn't the prediction, is because you can actually take that convolution. We're going to go down. So I like to reference both the sort of like, these are the layers in the initialization. This is how PyTorch organizes things. And then in the forward layer, you can actually see what would happen when you do the forward pass through that model. So you can see what happens is self.com0 happens here. It needs to know about the edge indices. And that's because otherwise it doesn't know which nodes are neighboring for any given node. So it takes into account, the input features or the node features and the edge indices, and then it computes the convolution. Then it actually, calls the ReLU, so it is nonlinear. This pop-up is killing me. And then it actually calls another convolution again. So after it does this once, it creates some sort of output feature. So I'm going to call that out of I here. So so we are no longer working with xi, we're working with out I. But then we can actually go ahead and do the same thing. So this is now out at index j equals 2, and this is now out at j equals 1. So reverse the order. And then you do the same deal. So instead of, xi, you have the output of the first layer at I, you have the output of the first layer at j equals 1 and 2. All of these have the ReLU function, the nonlinear function applied to it. And then you just go ahead and do another convolution. Like things are starting to get more abstract here, right? These are some weird combination of features that it's going to learn. But the idea is that like we want it to be able to do its job really well. And having, multiple layers often allows you to come up with a better representation. One critical thing, by the way, is that the number of inputs here was 2, right? We know that this had 2 inputs, but its output, actually, we specified some other parameter, a hyperparameter of the neural network called n hidden. So that's actually the number of hidden neurons or hidden states that it's going to have. So for out, it's going to be, out is going to, out of I is going to be of shape, n hidden, well, really batch size by n hidden. So, which is 128 in this case. Okay. So is that clear to like others? I'm not sure if this makes sense. What's happening is that you need to make your weight matrices such that it outputs something that's n hidden. It's not just 2-dimensional, because we're no longer talking about just a halo mass or Vmax. We're talking about some combination, some very nonlinear combination of those sorts of things, which is of size 128 in this case. And we can, you can try adjusting this parameter if you wish. So you do a second convolution now, which has many more features, and then you go ahead and do this computation again. And then finally at the end, I actually stuck in, I kind of made this a little more complicated, but I stuck in a fully connected layer, which goes from n hidden to n out. And so that the output here is just that single log stellar mass. And I also added I forgot I did this. I also added a shortcut layer here, which goes directly over here, and I just call that MLP. This is just a multi-layer perceptron. So this is basically like matrix multiplication, ReLU, matrix multiplication, and that's it. Okay, yeah, and there's a normalization layer, but don't worry about that. So there's a multi-layer perceptron that sort of skips the GNN part, and this basically should just learn, like if you knew nothing about the connectivity, it would still be able to learn basically the same thing that we just saw up here from the random forest. Hopefully that multi-layer perceptron, just a small neural network, will be able to learn this part regardless of whether or not we know anything about the connectivity. So even if you set it to 0, like the linking length to 0, and you say there are no neighbors for any nodes, it would still be able to learn something. And then the GNN through all this will learn something about the connectivity structure here. Okay, so that's what's happening. So so this is the fully connected here layer. This is the multi-layer perceptron if you look in the code. And I know that I'm starting to go through this a little more quickly now. And then we actually just add these two results, the output of the multi-layer perceptron with the fully connected network, which is really actually it's a part of the GNN, so I don't need to specify it outside of it. But it's happening there, and then you finally get your Y. If you remember from our training loop, we grab batches of data, which include X's, Y's, and the edge indices. In this case, we feed the data inputs into the GNN. It makes a prediction. So really, this should actually be P of I, right? Prediction for every node I. We then compare that against Y, which is the log stellar mass, our targets here. We can then evaluate how well it did. Since this is a regression problem, we can use something like a mean squared error loss. And then we do the back propagation, which updates our learnable parameters, which in that case are W1 and W2, as well as the weights in the multi-layer perceptron and the fully connected neural network. So I know there's a lot of moving pieces here, yeah, but again, I just want to go through all the bits in detail here before we go and initialize this model, which we're going to do now. A good exercise for you, and maybe I'll take a break here. I'll stop speaking for like 5 minutes and let you work through these two exercises here. The second one is definitely harder, but the first one is try and figure out what the dimensions of the inputs and the outputs are for each layer. And I sort of gave you a hint here talking about how the output after layer 1 is going to have something more like this. And then the second exercise here is to modify the graph Sage ConvNet, the neural network we just made, and we're actually going to try to concatenate these two things together, the multi-layer perceptron and the fully connected network, so that they sort of are a little more unified. And that might be a little bit trickier, but you can look at the answers if you get stuck, or talk to me or others. Okay, so the first part of this is to check what the shapes of the outputs are after each of these layers. Okay, and this is really important because otherwise it's a little tough to understand how these things are connecting together and how basically the features are flowing through the network. So with SageConv and for a lot of the PyTorch neural network layers, you can kind of see just by the way that you initialize, you can see what the shapes ought to be. And in fact, you could specify them that way too and have more control. So the number of inputs is 2 at each node, right? But the number of outputs here, you can see, is determined by after the first convolution layer. The first HConv layer is 128 because we've used this parameter and hidden set to 128. And the total shape as information flows through will be batch size by 128. But in this case, we should think of it as every example gets a 128-dimensional feature vector. So inputs are 2, BS by 2, batch size by 2. Outputs are batch size by 128 because that's what we set and hidden to. For the second convolution, the inputs and the outputs are both 128-dimensional feature vectors. So that's the output size there. For the fully connected layer here, denoted by FC, the number of outputs is however many we specify here, because we're trying to regress just a single variable. That's just 1. So number of outputs here is 1, even though the number of inputs, that linear layer, is 128. And then finally, there's an MLP. So it goes through, it basically, you feed in those 2 features, it produces 128 hidden, like a hidden feature vector of 128, applies that nonlinearity, and then it goes and does another matrix multiplication, which changes its shape from 128 back down to 1 as well. So the answers then are, it would be basically of shape 128 and after column 1, 128 after column 2, and then after fully connected and after the MLP, it should be of shape 1. The second exercise is a little bit trickier. So we're going to remove the fully connected layer here. And what we do, and maybe I'll just show it here, is we've got, if we take this out, by the way, if you hit Command and then the slash, like the question mark slash, you can actually toggle whether or not you're commenting something out. So that's a handy trick to know. So if we take that out, well, we know that the self.fully connected layer is in use here, so we can no longer make use of that. So let's keep track of this. So this is the output of the convolutions, but we want to create a fully connected layer that instead uses the MLP. So what we can then do is we can actually concatenate stuff. I think is it torch.cat or is it torch.cutcat? Concat or just cat? Cat. Yeah, just cat. Yes, thank you. I put that hint in there for myself, really, because I can't remember these things. And then the other question is like, which dimension do you want to, basically concatenate along? And I'm going to cheat because I don't remember. It's along the negative first direction. Okay, so this is another thing that's like remembering is that so negative first just means the last dimension. You're going to concatenate along the last dimension. So in other words, if you have like a big, if you have one column vector or like 128 features, like I think of them as columns, you want those columns to be, next to each other. You want this column and then that set of columns. You don't want them to stack them like row wise, because that is a stacking along along the examples, basically the batches. And so you can actually write dim equals 1 because this is the column, along the column axis is how you're doing a concatenation. You can do 1 because there's only 0 or 1, or you can do -1, which I usually do because it's along the last axis. So we're going to go ahead and comment this part out. We're going to still take the ReLU of this, which is important. And then I'm going to go and just delete that. Now, will this work? Or did we forget something else? Because I'm ominously saying it. The other thing that we need to do actually is this MLP, we said only has 2 inputs, but remember that we want to concatenate in the fully connected neural network here. So this actually you need to add another 128 inputs into that MLP in order for it to work. Otherwise, the shapes will not match up. There was a suggestion, by the way, which I thought was actually quite clever, is that you could also, somebody asked, why don't you also take, X1 and stick that in here? And indeed, you can. You could do something like this, and you can actually just concatenate those 3 things in there. So then what you're doing is you're really taking X1, you're grabbing also like a skip connection from the middle of that set of convolution, the sage comms in here, and you're going and basically letting that also contribute to the final estimate of the prediction. Effectively, you're just propagating information, allowing it to flow more freely. Otherwise, it has to go through that second stage comm, and potentially it could get changed. And maybe if you take a neural network and you just keep appending layers to it, at some point you're going to just like make it really noisy, and it'll be kind of hard to learn or to train it. And so actually having these skip connections is not a bad idea. And so if we were to do that, then we actually want 2 and hiddens in here, 1 for X1 and 1 for X2. And so hopefully this will work. Let's see. Well, I guess we'll see in a moment. So then, so that's one answer. And then I basically created the training loop. So if you remember my diagram, like the flow chart from yesterday, that's a more general framework of saying, how does stuff work? You have a model, it could be a CNN, it could be a GNN here. You pass it in, you pass your inputs in, you make a prediction, and you also keep track of the label, and you evaluate the loss. And then by having a loss, defined using like a torch, a torch function, you can, and also a convolutional or a neural network that has the gradients attached to it, you can then make the back propagation and therefore update the neural network. So that's what we're going to do here. let's see. And technical point here, we actually just have a single like giant graph, right? We made this giant graph. It has 300,000 nodes. It has 8 million edges. It will not fit into memory if you just try to cram the whole thing on a GPU or even or on your regular RAM. And so we need to use a data loader that actually just grabs random nodes. And then, so for each node, it will grab it, and it will also snag all of its corresponding edges, and that is things that are in the neighborhood of that node, and it will use that for training. However, we've already allocated certain nodes into a training set and a validation set. So we're going to go and take a subgraph, that is the data.subgraph, to grab only the training indices that we specify for data, and we're going to put that in the train loader. And then for the validation loader, we're going to do same thing, but data.subgraph validation indices. For some funny reason, in PyTorch geometric, they use num parts rather than batch size, but it's basically just the same thing. The batch size times the number of parts, basically the number of how much you divide your graph into, the number of parts of your graph, has to multiply up and become like the training index. So anyway, so that's just another thing there. But you can read up on the documentation. We go ahead and run that, and then let's see the moment of truth. Does this actually work? Okay, well, something's happening. So this is the training loop. It's actually very, very similar to what we saw last time. You can see I'm basically predicting for each epoch. It's training very quickly. This is on a CPU, by the way. So this is a pretty lightweight neural network. It's probably got of order like, I don't know, like 10,000 parameters or something like that, rather than like the 10 million that we saw in the last one. That's why I'm not using the GPU. But you can see it's actually the loss. I'm sorry. So the training and validation loss that I used here is the mean squared error. And then I actually report the root mean squared error. So it's literally just the square root of the loss for the validation set in this last column here. And so you can see that it steadily declines as I'm reporting the outputs. You can also, actually, hold on. Yeah, so you can also plot these, to get a sense of what the training and validation losses look like. And you can see they start off extremely high. In the beginning, it doesn't know what it's doing, and then it drops down and does much better. So just good to look at that. Let's go with 0.5. So we can change the X scale. Oh, it had a weird blip towards the end. But anyhow, you can see that it is learning, to perform pretty well. And then when we look at our final results, we get something like a root mean squared error of 0.178. If you recall, I think the baseline method that we had with the random forest is 0.186 or something like that. So this is doing a little bit better. What is the reason that it's doing better? The random forest actually does a really good job of learning the galaxy halo connection by itself. So any extra information that we can learn is actually because we're leveraging the connectivity here. Like, so what we can say, at least just from this model, is that there is information, clustering information on large scales beyond the virial radius. The virial radius of like a typical massive galaxy is like less than 1 megaparsec. It's like 0.3 megaparsecs or something. But we're looking at scales of up to 5 megaparsecs, and we're saying that keeping track of that information and the cosmic connectivity of those subhalos is informative for telling you something about the baryonic properties as well. And so anyhow, so that is that's one result that we can already we can already report on here. So this is our simple GNN. I know again that there's a lot of complexity that goes into it. So just to review what we've done here, scrolling through too much stuff, we have created a graph, and this is a PyTorch geometric data object. The graph contains nodes. Those nodes have features on them, and these are just the subhalo features, like the halo mass and the maximum velocity of particles in each halo. We are trying to estimate the stellar mass of every single subhalo, for these relatively massive halos in the simulation. We then, because we noted their positions, we were able to create the edges between galaxies or subhalos that were within 5 megaparsecs of each other and define their neighborhood. And so then when we iterate through our data loader, that operates on this data object, we can then get not just the individual nodes and their predictions, but also the connections to other nodes and their features as well. Leverage the information there by using a SageCom for just any sort of graph, essentially any graph layer. And so the graph layer must be permutation invariant. So no matter how many neighbors are present for each individual node, it needs to aggregate that information down into a consistent shape. And it also needs to not care about the ordering of that. And then finally, it takes that information, its neighbors, as well as the information of its own node, and then goes and does some neural network magic, which we can make infinitely more complex. But at the end of the day, it's just trying to make that prediction on that specific node. And then we can go and, as we've done here, you define a loss function, you compare the inputs and outputs, or predictions and the targets, and then you use, you let PyTorch go and update the neural network weights in order to learn a function. It represents it. So, so this is, this is all there is to graph neural networks. Easy. No, there's actually so much more. There's so much more. I mean, there's, like we could try to predict things on edges. You could create graph data sets for all sorts of different types of, astronomy data, and many of which haven't been realized yet. So my background was in radio interferometry. I mean, radio telescopes on a grid where you care about the baselines and look at the, the Fourier, transform of the signal is actually something that's very, very well suited for graph neural networks. I don't have the time to do that, but like somebody probably could do that and make an interesting statement about how how radio interferometry and reducing radio data could go in the next couple of years. But I'm just like throwing ideas out there. There are a lot of possibilities, and if you kind of go down, you can also see an example of a far more complicated graph neural network. This is much more closely aligned to the neural network that I designed in my in the paper that I mentioned here. And the key difference in that case is that we actually make use of the edge attributes as well. So this one, remember, this only looks at x, j, and xi. But imagine you have edge attributes e sub ij, so for any pair of nodes, you also have features that are over here. You can then take into account those features. You have to aggregate over ij as well. And you can see through this kind of complicated neural network that you can create these edge interaction layers, which then, to keep into account features on edges as well as features on other neighboring nodes, and then propagate that information around. There's also an option to make those networks deeper. So I can actually not just do this, but I can also then, basically go one step beyond, and I can say that, this feature here or this node here can then be aggregated onto, a hidden state for this, which then propagates back up here. And so that's basically the idea of adding more layers to graph neural networks that expands the reach of, like what is considered a neighbor, and therefore you could leverage more information. That could be good, that could be bad, but that's just a possibility. So I've given an example which is a lot more complicated here, but you can kind of look through it, or feel free to ask me questions about it. And what you can find too is that the training is better. It's a much more there's just a lot more details to this model, and we can do a little bit better in terms of the root mean squared error. And then finally, there are other things that you can do, things like adding data augmentation. So for instance, we talked about with the convolutional neural network, you might want to like do rotations or flips or things like that, just to augment the data. It turns out that with neural networks, if you add a small amount of scatter into, for example, along the edge and on the node features, that actually tends to help you learn a more robust model. And then I've also got so there's an answer to that question. I have another challenge question, which is like, it would be an active research problem, which is like try to use a heterogeneous data set and see if you can learn something different for central satellite subhalos. That is far beyond the scope of what we can talk about today, but floor is all yours in order to make the most of these tools. So thanks again for listening. And it's been a pleasure to talk to you about convolutional and graph neural networks. And feel free always to bother me later. So, thanks.